We are going to talk about permutations today, and permutations form groups. As you can see in the notes, a permutation of a set S is a one-to-one function from a set S to itself. So on the side of this slide here, I've drawn a set S. It's the numbers 1 through 5. We're going to write down a function sigma that's one-to-one and onto, and I've assigned 1, 3, 4, and 5 to the outputs 1, 5, 2, and 4 respectively. Now, because I need this to be a function, I have to assign 2 to something. I can't leave any elements of my domain unassigned. Because I need it to be one-to-one and onto, well, if I want it to be one-to-one, I can't assign 2 to any of the numbers 1, 2, 4, or 5, because those already come from someone. And I have to assign something to 3, so I'm going to assign 2 to 3, and then I get a function that is one-to-one and onto. Now you might be asking, we've spent so much time on automorphisms, what does this have to do with automorphisms? Well, let me tell you a little bit more about that. Let's take a function, a polynomial p of x in f bracket x, where f is some subfield of the complex numbers. By the fundamental theorem of algebra, this polynomial will have roots, a1 through an, in the complex numbers. If f is a member of the Galois group of f adjoin the roots of p of x over f, then, well, we know that f is an automorphism from f of p of x to itself that fixes f, and so the only things that get to move around are the roots, and then we put them together with combinations of elements of f, and, we send stuff to places depending on where those roots go. What that means is that f is really a permutation of a1 through an. So f can be thought of as a one-to-one and onto function from the roots of p of x to themselves. And this is how we think about f as a permutation of roots. And we sometimes call f restricted to the roots the restriction of f to the set of roots. Now, as it happens, the set of permutations of a set x is a group with respect to composition of functions. And I'll tell you more about composition of functions on the next slide. But if x, the set, has at least 3 elements, we do not get a commutative group. There are going to be elements that, when we switch their order, they give us different permutations. So we'll take a look at that on the next slide. Okay, here's your reminder about how composition of functions works. Let's say that we've got 2 permutations of the set of numbers 1, 2, and 3. So sigma and gamma are both permutations, and I've defined them for you here. I want to just pick on a few specific ones. So sigma of 1 is 1, we say sigma fixes 1, sigma of 2 is 3, and sigma of 3 is 2. So it switches 2 and 3 around. Sigma of 1 is 3, sigma of 2 is 1, and sigma of 3 is 2. So it shuffles everything around. Now, when we compose sigma and gamma, it's going to give us a function from 1, 2, 3 to 1, 2, 3. And here's how that function actually works. Well, since it's a function from 1, 2, 3 to itself, we're going to have to be able to plug in 1, 2, and 3 to this function. And when we do that, I'm hoping it's a permutation again. So I'm hoping that it's a one-to-one and onto function to the set 1, 2, 3, because I want this set of permutations from 1, 2, 3 to itself to form a group. So I need it to be closed, i.e. I need to compose 2 of my permutation functions, and get another permutation function. Well, the way that we plug 1, 2, and 3 into the composition is first we plug 1 into gamma, and then we plug gamma of 1 into sigma, and the same with 2 and 3. When we actually do this, we get sigma of 3, sigma of 1, and sigma of 2 as our outputs. And so the composition function, sigma of gamma of 1, gives us 2, and sigma of gamma of 2 gives us 1, and sigma of gamma of 3 gives us 3. So now 3 is fixed. Is it one-to-one and onto? Yep. So it's another permutation. That tells us that our permutations are closed under composition. Well, this gives you an example that shows that there's evidence that that's true. It is true in general. Just to belabor the point, we compose permutations, we get another permutation. And that means that permutations, the set of permutations from a set X to itself, satisfy the group axiom G1 for the operation function composition. Let's think about the other group axioms. What about G2? Well, we need our function composition to be associative. Okay, so here I've picked out 3 permutations. I've got sigma, gamma, and theta. When I plug in A, essentially what this is saying is, okay, first plug A into the gamma of theta, and then plug that into sigma, and this really boils down to sigma of gamma of theta of A, and we can rearrange the composition. And we'll get the same function back at the end of the day. You're probably used to functions being associative from the way that you've dealt with them before in your mathematical life, like in calculus. Now, since this is true for all elements of the set S of elements that we're permuting, we know that the function sigma gamma of theta is the same as the function, sigma of gamma of theta. And therefore, function composition is associative. All right, G3, do we have an identity? Well, the permutation that just sends everything to itself is the identity permutation for function composition because of the way it composes with other functions. Let's take a look. Sigma of E of A is sigma of E of A, which is sigma of A for all A and S. So sigma of A is just whatever sigma does to A. And that means that sigma of E is the function sigma. And the same is true if we compose them in the opposite order. And the last thing we need to worry about is whether or not we have inverse permutations. But it's kind of believable that we would, right? If we permute things, then just unpermute them, and that should be the inverse. And in fact, that's true. But more generally, because we have a function from a set to itself that's one-to-one and onto, we know that we have an inverse function. And what does it mean for that to be an inverse function? It means that when we compose them in either order, we get the identity function that doesn't do anything. So, do we have G5? Do we know that permutations commute with each other? Alas, we don't if the size of our set X is 3 or more. Now, I know you're all fans of my cute drawings of permutations as sets written from one side of the page to the other with arrows attaching them, but if we have a lot of elements, it's kind of hard to figure out how those permutations work. So we want to introduce cycle notation, which is a way of writing down permutations so that we can see what they do without them taking up a huge amount of space. I mean, if you just look at the size of the displayed permutations on this page in display math mode, they're pretty gross to write down, and they take up a lot of space. Okay, before we jump into cycle notation, I want to highlight this notation S sub n. This is really a way of just saying we're going to look at the set of the group, in fact, of permutations of n things. Usually we think of those n things as the numbers 1 through n, but as we noticed before, an element of a Galois group might be a permutation of n roots. And so we'll have a way to identify permutations of roots with elements of these groups S sub n. So Sn, sometimes called the symmetric group on n elements. Okay, so what are we doing with these cycles? Here I've written down the cycle 1, 3, 4, 2, 5. So in parentheses, I have parentheses 1, 3, 4, end parenthesis, open parenthesis, 2, 5, end parenthesis. All right, what the heck does that mean? Well, if it's going to mean anything useful to us, it's got to be a function, which means I should be able to, for example, plug in 1 and see what I get when I plug in 1. The way to read the cycle is you find 1 and you see where it goes by looking one place to the right. And so when we plug in 1, we get 3. And if we plug in 3, we see that 3 gives us 4. What happens when we plug in 4? Well, we hit a parenthesis, but that really just means go back to the beginning, so 4 goes back to 1. So we can think of 1, 3, 4 as a little 3 cycle. 1 goes to 3, 3 goes to 4, and 4 goes back to 1. Or a tricycle, if you like. Insert tricycle beeping noise, which I haven't been able to find online. Well, what about that other set of parentheses? Let's plug in 2. We see that 2 goes to 5. If we plug in 5, 5 goes back to 2. Oh, and if we tried to plug in 6, or 0, or -18, or pi, or whatever, This doesn't do anything to those because they're not part of cycles. We could think of those as belonging to, I don't know, unicycles or cycles of one element. They get fixed by this permutation. So probably this is an element of S sub 5, the permutations of the things 1 through 5, but maybe it's an element of S sub 6, and we are thinking of 6 as being an allowed input, but this cycle, this product of cycles, doesn't do anything to the number 6. Anyway, as one of those little function schematic diagrams I've been drawing, this is what it looks like, and you can see why cycle notation might be preferable to long arrows and multiple colors and all that good stuff. Now, here's some more terminology. The cycles 1, 3, 4 and the bicycle or 2 cycle 2, 5 are called disjoint. And that just means that there are no numbers in common in the different sets of parentheses. Right, so I see 1 in only one set of parentheses, I see 3 in only one set of parentheses, etc. Now, if you'll indulge me and look back over at the notes, we can combine disjoint cycles, and that's what we did in our little example. The example on the page is we have a function that switches 1 and 2, a function that switches 4 and 5, and 3 gets fixed. And so to write this in cycle notation, we're going to write it as 1, 2, 3, 4, 5, but because 3 doesn't go in, we're just going to omit it. And this is where you should laugh at my joke about unicycles. Ha ha ha, if we were in class together, we'd be having a grand old time right now. Okay, last bit of notation, the identity function in SN, when you're writing it in a tech document, for instance, is called iota, which is like an I without the dot. But if you're writing it on the board or in your notes, I prefer E because it's a little bit easier to actually see what it is. Now, we've talked about these disjoint cycles, and we've done examples with disjoint cycles, but we need to figure out what to do if we want to compose 2 cycles that are not disjoint. So if we have functions, then we've got to be able to compose them in our group S sub n. So let's look at how that works. Okay, here's how we're going to do cycle multiplication. We call it multiplication instead of composition because we write the cycles next to each other, so it looks like multiplication, but really, if you get confused about what's going on, it helps to come back to the fact that this is really function composition. We plug in inputs on the right of the function, and we trace through what happens to them as we go from right to left. Okay, so I've written down 2 cycles. One of them is a 4 cycle, one of them is a 3 cycle, and these cycles are not disjoint because they both have 3 and 6 in them. So let's see what happens when I plug in 1. Well, I plug in 1 on the right. The first cycle, 3, 6, 5, that 1 gets plugged into, doesn't do anything to 1. So 1 comes out unscathed. We just get 1 back. And then we plug 1 into the second cycle, which sends 1 to 3. So we see that the first part of the cycle that we're going to get involving 1 sends 1 to 3. And now, to figure out what comes next, we're going to plug in 3. Okay, well, 3 goes to 6. 6 goes back to 1, so we end our parentheses here. And if we think about what's going on with 2, well, none of the cycles involve 2, so 2 is fixed. Now, let's plug in 4. The first cycle that we plug it into, 3, 6, 5, fixes 4. So then we plug 4 into the second cycle, and 4 goes to 6. Now we plug in 6. 6 goes to 5 in the first cycle that we plug it into, and then 6 goes nowhere in that second cycle, 1, 3, 4, 6. Sorry, 5 goes nowhere in that second cycle, 1, 3, 4, 6. So 6 goes to 5 in the composition. And when we plug in 5, we get 5 goes to 3, and 3 goes to 4, and so we're going to end our parentheses there. And at this point, we have used up all the numbers that we saw in those cycles. We have 1, 3 as a 2 cycle, and 4, 6, 5 as a 3 cycle, and that's it. That's our disjoint product of cycles representing what this function does. So what do we do more generally? Well, let's think of them as functions for a moment. If I have 3 permutations, sigma of gamma of theta, I can plug something in and follow it through that function. So first I plug it into theta, then I take the output that I got there, I plug that output into gamma, I take the output that I got from gamma and I plug it into sigma, and then I hit the wall. I like to think of this as running into a wall. I don't know why. Probably some sort of, weird desire to punish myself for something. Okay, anyway, we plugged it in, we hit the wall, and so that's our final output. That output, we plug it back into theta, and we track where it goes. We get a new output, write that down. We take that output, plug it back in, until we get to a point where we would repeat a number, and then we close our parentheses, and we find something we haven't plugged in already. There's some more examples here if you want to see what happens when we compose these big long products of non-disjoint permutations. And here we have a word about inverses. If we want to write down the inverse of a permutation, like say 1, 2, 3, 4, as in the notes, we just reverse it. It would be 4, 3, 2, 1. But we like to write things down so that the smallest number in our parentheses comes first, so we just cycle it around. So we know that 1 goes to 4, and then 4 goes to 3, and 3 goes to 2, and then 2 goes back to 1. So we would write the inverse of the permutation 1, 2, 3, 4 as 1, 4, 3, 2. When we're working with products of permutations and we want to deal with them as cycles, because they don't commute with each other necessarily unless they're disjoint, we have to invert the order of them to get the inverse. So in our example 1, 2, 3, 4, 6, 5, 1, 2, the inverse of that product is going to be 1, 2 inverse, 4, 6, 5 inverse, and 1, 2, 3 inverse. We can work that out in a couple of steps and then rewrite it according to the conventions for writing down cycles with the smallest number first. And we end up with the permutation 1, 3, 4, 5, 6 as the inverse for this product of non-disjoint cycles. Oh, by the way, if you wanted to know what the original cycle was in disjoint form, you can take the inverse of 1, 3, 4, 5, 6. Okay, take a look at this proof here. The proof that disjoint cycles commute. This is a good template for how to do proofs involving cycles and permutations. We're going to use this idea in some of the writing assignments that we do in the semester. So as usual, if you have questions, post them on Piazza. Oh hey, how many elements does Sn have? Well, it's the number of ways we can rearrange n things, which we tend to call n factorial. And that's our rip-roaring video on permutations. See you next time. Stay healthy.